So if we have a curve, there are going to be many different possible parametrizations of this curve. So a parametrization might send the number 0 here, number 1 here, number 2 here, and so forth. But a different parametrization might send the number 0 here, -1 here, maybe -2, -3, -4. So it'll be moving very slowly for a bit and then very quickly. Or the parametrization might even go in the opposite direction, like we might have plus, 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 negative, and negative. So we'll especially be, sometimes we'll say a directed curve if we want to specify in advance that it should sort of be increasing this way. Anyway, we should think about different parametrizations as these are sort of different coordinates for the curve. So we talked a little bit about different coordinate systems at the beginning of the course. This is a different type of coordinate system. These are like nonlinear coordinates. So it's not sort of the coordinates that we're using for the entire space, R3, but it's a way of describing points on this specific curve with numbers. So there's many different coordinate systems. If we just sort of get a curve, is there sort of a canonical or most natural coordinate system? And so the answer to this is yes, there is the arc length parametrization. This is maybe a needlessly abstract way to motivate this concept, but this is maybe a way mathematicians would what we like about this. So the arc length parametrization, so if we start out with a curve, then at least if we fix a direction and we fix a base point, so we decide where 0 will go, then a natural parametrization of this would be to send, so 1, if we enforce that the curve length between, basically that the length of the curve, so we'll use s as the variable for arc length at or from r of 0 to r of s is precisely s. And if we plugged in a negative value of s, then it would be like length of 2, but in the opposite direction. So this is why we've also chosen a directionality. So this we call the arc length parametrization with respect to the chosen origin point. So S arc length, how do we calculate that? Well, basically just from our definitions already. So if we start out with this curve given to us as r of t instead of r of s, so now t is just any parametrization of this, and s is the arc length. So maybe the notation r of, it's really these two functions are going to be different different vector functions, I guess. But so the formula for arc length as a function of t, this just by what we've already this just by our definitions, this will be from t0 to t, length r prime of t dt. So here t0 is chosen so that this point here is r of t0. So to find the arc length parametrization, we would have to solve for, so if we were given a parametrization, then to find the arc length parametrization exactly, we would need to solve for t in this equation, or from solve for t in terms of s. So this is something that we generally cannot do. I'll give some examples in a second where we can, but it's very rare that we can come up with an analytical formula for the arc length parametrization. On the other hand, it's very easy for a computer to calculate the arc length parametrization, and indeed, this is used quite a lot in graphics. So here's an example of that. I've got a curve, and I don't have a formula for this curve. I just drew it in Inkscape and exported it. And I'm going to animate this car moving along the curve. So that was using the arc length parametrization. This is just something built in that I can load a graphic or load a path and ask the computer, give me the point at position whatever along this curve, and it'll calculate that for us. Notice that I also needed to know the tangent vector of the direction of the car in order for it to point in the correct direction along its journey. But I didn't really need to know the full tangent vector. I only needed to know the direction of the tangent vector. So the magnitude was not important, although the direction, the sign, was. So this information would be equivalent to knowing the unit tangent vector. So here are a couple other parametrizations of the same curve. Here, it's accelerating and decelerating at the beginning and end of its motion, so it looks like a more natural motion. And here's an easing out animation where it's just decelerating towards the end. Okay, let me finally do an example, or a real example. So let's let r of t be 3 cos t I plus 2tj plus 3 sine of t k. So here's what that'll look like. Then we'll find the tangent vector. So this will be negative 3 sine ti plus 2j plus 3 cosine t k. So here's that tangent vector. Now let's find the magnitude of that. So that'll be square root, so sine squared plus cos squared is 1. So square root 3 squared plus 2 squared is root 13. So now we can calculate the arc length. So s is a function of t. The integral, let's take 0 to be our base point, to t, length of r. So I'm going to use tau for the integration variable. This is integral 0 to t of root 13 d tau. So we get that s is equal to root 13 t. So now we can go and find the arc length parametrization. It's very rare that we can do that, but in this case, since we solved for s, s is just a multiple of t, we get r of s is 3 cos s over root 13 I plus 2s over root 13j plus 3 sine s over root 13k. Or here's another example. So we'll let r of t be negative e to the t I plus e to the t sine t j plus e to the t cos t k. So here's that curve. Now let's find the tangent vector. This is r prime of t is negative e to the t I plus, and then we've already, so e to the t sine t plus cos t j plus e to the t, this will be cos t minus sine t k. So here's those tangent vectors, and I've also drawn the unit tangent vector in blue. So now the arc length of that will be square root, so e to the t, or e to the 2t for the first term, and then we already saw an example like this where these will have some cross terms canceling out, and then sine squared plus cos squared. So this will just work out to be this stuff squared is just e to the 2t. So this becomes root 2 e to the t. So now we can get an expression for s. So s of t is integral, go from 0 to t, of root 2 e to the tau d tau. So this will be root 2 e to the tau t0 is root 2 e to the t minus 1. So we get that t s over root 2 plus 1 is equal to e to the t, and so t is ln of this. So we can now write down the arc length parametrization. So let me erase some of this. This will look a little bit uglier than the last one we did. But so we'll get r of s is negative s over root 2 plus 1 I plus s over root 2 plus 1 sine ln s over root 2 plus 1 j plus s over root 2 plus 1 cos ln s over root 2 plus 1 k. So not a very nice expression, but very useful conceptually and practically.